All right, so for the second half of this session, we've got two more talks, and Leonard's going to give us kind of a more in-depth look at our 2D magnetic maps. So give it off to him.
Sure. Thanks, Shay. Well, thanks for the invite again. So I would like to take you, well, more or less, it's more almost a parallel talk to what Eduardo just already showed us. So traditionally, information about the geomagnetic field comes from bulk samples, preferably these one-inch cores. And these high-end magnetic surface scans, they have always been the realm of very fundamental rock magnetic studies like MFM studies or bitter patterns. But over the past decade or so, the introduction of the quantum diamond microscope kind of greatly eased the acquisition of magnetic surface scans, and also enable the quantitative assessment of the magnetic moment of samples at a micrometer scale. And such scans showed their potential already, or proved their potential already in studies in meteorites and zircons. But that is not really, like our bulk samples in the world are like rock samples from like either volcanics or sediments. Sediments, they have very small grain sizes, so that's a stretch. So, well, I was thinking of, basically this entire project was rooted in my own frustration about having to chuck away 80% of my paleo intensity data during my PhD. That was basically my go-to for this entire project. Because in a volcanic, there are so many different grains with different composition, different shapes, different sizes. And only like a few large grains would already mess up your entire experiment and render your paleo intensity data uninterpretable. So if you would only be able to kind of determine magnetic moments of individual grains in a sample, we would kind of select maybe grains that we rely or that we trust and interpret only their signal, or maybe we can weed out grains that we do not trust, like the really large ones, for example, or ones that show viscous behavior. So that's what when I was thinking, like, hey, we could just, if we use these new magnetic scanning techniques, then we might do that. But then I ran quickly into an issue with the number of grains that are in a sample. So the examples that Eduardo already gave, we have like probably usually small isolated sources that are, well, properly in view. But if we look at a volcanic sample, then we have easily thousands of, maybe millions of individual iron oxide grains in every square millimeter of sample. So that challenges these inversions quite a bit. So let's have a look. We've already seen this this thing earlier today. This is the one in Utrecht where we have it up and running right now. Usually my summary of this machine is that it combines a microwave, a diamond, and a laser to measure magnetic signals, and that's usually enough to spark interest of our students. But for the technical details, I refer you to the poster by QDMIO later today. But do keep in mind, that's important, that a QDM is an optical technique. So we're actually looking at light. So we're looking at very subtle changes in light, in the fluorescence as function of a microwave frequency, and that gives information about the magnetic flux or the magnetic signal in a distinct layer in a diamond chip. That is the take-home message of how a QDM basically works. So then we have a two-dimensional map of the magnetizations above our sample. And then we end up in with this guy, Oliver Kellogg, mathematician, 1929. He wrote this book, Foundations of Potential Theory, and there it is stated that this kind of inversion problems are by nature inherently non-unique. That means that if you have a magnetic scan over a surface and you have no additional information, or you don't make any additional assumptions, you can get an infinite number of solutions, an infinite number of magnetic configurations in your sample that could satisfy your magnetic surface scan. So that would basically be the end of it. But luckily, you can either constrain, like put assumptions on your inversion model, or you could add additional data. So in a case where we have a relatively simple or relatively isolated magnetic anomaly on top of our sample, we can use, well, the techniques that Eduardo showed to fit like a dipole or even a circular harmonic solution. So if we assume that we have like one source underneath our anomaly, we can calculate what that source, or what the magnetization of that source would be. But if we are looking at a more complex scan, and this one is not even that complex, but we have like a couple of distinct anomalies, and above all, we don't have a clue about what's in our sample, what is right there. In that case, your inversion is lost, and you cannot determine any information on the magnetizations of your grains in there. So what we need to do is tell the inversion where our magnetic sources are. That would greatly improve the inversion, or to make the whole inversion basically unique. So what we did is we took our sample and we put it in a micro-CT, because the good thing of iron oxides is that their density is approximately twice as high compared to the other minerals that are prominent in the volcanic rock. So if we now combine our magnetic scan with our micro-CT scan, we now know where we should put our magnetizations. And that means that this inversion all of a sudden becomes a unique problem, and we can determine the magnetizations of our individual grains. This is basically the master thesis of Anna Marika back in 2015. So since then, we took this further, and I would like to tell you a lot about the progress that we made so far. So a short summary of this technique, technique we now call magnetic tomography. So we start off with two data sets. The first data set is our magnetic surface scan, and that can be a scanning script microscope scan. It can be an MTJ, magnetic tunneling junction, or a QDM, doesn't matter. But importantly, we also add spatial data from a micro-CT or a nano-CT, and if you would really go down to a FIB-SEM, but that means you lose your sample. That's a bit of a problem. And then really importantly, you have to co-register these two data sets in one coordinate system. And when we started this, we thought, well, this is easy. Well, you know, you measure one thing, you measure another, you put them on top of each other, and then all of a sudden, one micron in one machine is something completely different than the same micron in a different machine. So you have to scale and you have to tweak to get those two data sets to fit. Then we do the inversion, and then we get the magnetizations per grain. So this is the input, and that would be the result of a magnetic tomography experiment. To see how well our magnetizations resolve the magnetic flux on the surface, we do a little check where we take our magnetizations and the spatial data. So we assign each grain that we know of its magnetization. We calculate what the magnetic flux, what the magnetic map on top of the sample would look like given these magnetizations. That's the model surface magnetizations. And then we subtract that map from the actual magnetic scan. So then we are left with the residuals that our inversion cannot explain. So what does it look like? Here on the top left, there is a synthetic sample with 8 individual sources. And here is a volcanic sample that is slightly more complex because it has 1646 individual sources. So all these magnetic grains are outlined here in black, there in white, and the magnetic scan is put on top of each other, on top of this. This is was published very recently, earlier this year. Here we see that all these magnetic sources, all these magnetic grains, they are close to each other. They can be on top of each other, and this is why your inversion struggles if you do not add the locations of these magnetic grains to your inversion. this is the work of Marta, as I said. So far, so good. That would mean that we solved this problem and that we could now do inversions for all our volcanic rocks. Of course, it's not that easy. First thing we need to consider, there are a couple of challenges I want to discuss with you today and also how we try to work around them. The first thing we need to consider is the characterization of our sensors. So the QDM maps are pixels. So it's just a pixel, and these pixels have a surface area, quite often of 1.17 or 1.17 micron. But if you consider them to be point sources, then your whole geometry changes, because the sample sensor distance is only a couple of micron, your grains are a couple of micron, and your sensor size, your pixel size is like 1 by 1 micron. So they're all in the same range of sizes. So you cannot just make your pixels into a point source. Then there is a sensor sample positioning. If you position your sample and you're going to use it for an inversion, you have to know your positioning really, really precise. Again, we were talking already in microns. So a micron is already a lot. That's not enough precision to know it's, to actually map the two coordinate systems. And also you have to be absolutely sure that's plane parallel, so that your surface of your sample is absolutely parallel to the surface of your diamond. Otherwise, it's slanted and then that propagates into your inversion. And then lastly, a thing that is really important to consider is that the micro-CT has a resolution, a lower limit to its resolution. Currently, we're using micro-CT scans with a resolution of 350 nanometers. But that means that all grains that are much smaller, that are smaller than that, or either smaller than half a micron, just don't show up. You don't resolve them in your micro-CT scan. And there is still an order of magnitude to go until you're down to 40 nanometers, where you would, below that, you would guess that your grains are super paramagnetic and do not carry a remnants. So there's still an order of magnitude. And that is the big black box that we have been running into, bumping into actually over the past 2-3 years. So these are the 3 things that I would like to discuss with you. So first, it's a sensor characterization. In our first routines that we used, we thought, well, it's just a point sensor. You just put it like at one point, and then that saves you a lot of computational time. But of course, these pixels, they have a surface. So that's when we changed our inversion routines to actually include this surface integral over the pixels. So that actually improves the inversion quite a bit. But then these QDMs have a diamond chip where there is a layer of MV centers. And in the diamond chips that we generally use for geological applications, this layer can be more than a micron thick in itself. So that's when my postdoc said, well, if I'm programming 2 integrals, I can also make it 3, and then we have a volume sensor. So that's when we, so for our inversions, we consider the sensors to be like a volume. We have a thickness, and that thickness, well, it's here depicted as almost flat, but if you reckon that your pixels are 1 by 1 micron and that layer of MV center is a micron thick, then that means that your sensors are actually almost cubes, so they're not that flat. Also, this gives the opportunity, it was briefly touched upon by Eduardo, to include the 1-on-1 axis of your QDM instead of just the BZ projection, because for the volume integral, it doesn't matter. So we have to be careful with characterizing our sensors. Then there is a sensor sample positioning. We were, well, usually previously these things were done by hand using a couple of actuators, but that was not precise enough. And we were always dreaded to break the diamond. These diamonds are almost the most expensive part, so we didn't want to turn knobs underneath it. So that was when our technician came up with James. We call this thing James. We don't know why. It's, well, I know why. It's a Dutch acronym, and it was born out of frustration, so I'm not going to repeat it here. We have James, and James is a 5 axial sample positioning system. So X, Y, Z, and 2 tilting axes. And the good thing is that you see here, you see 2 of the 3 load cells. And as soon as there's more than 0.5 gram of pressure on that thing, the thing stops moving. So that means that we reduce the risk of breaking the diamond, but it also means that by some iterative approach, we can actually use the tilt sensors to actually put that sample fully planned parallel to the sensor, to the diamond. The actuators have a resolution of like 10 nanometers, so it's actually pretty much flat. We put like a dovetail connector on top of it, and our technician had only one request when we started this project, and that he got like funding for his own 3D printer. So we gave him that, and now he can 3D print sample holders for each and everything that people may bring into the lab. So by using James, we actually get a sample fully flat, planned parallel, positioned against the diamond without any risk of breaking the diamond, which is a good thing in the lab. So this is the technician who built it. But then, more importantly, because these two things were solvable either using improving your inversion or by hardware, but then these ghost grains. And we noticed that this became like the question that was always popping up, like, hey, maybe you don't see your grains, and then everything is, your entire inversion breaks down. So what we did, we took a sample of a piece of our sample, and we made a FIB-SEM scan out of it. So this FIB-SEM, focused ion beam, we made slice and view technique, with a resolution of 20 nanometers. So that means that we see each and every iron oxide grain that can carry a remnant magnetization. First thing we noticed is that these tiny iron oxide grains are all, they all live on the interfaces between larger minerals. Also from a geochemical perspective, that's not really that weird, because these tiny grains, they crystallize the latest. So they're all bound to these interfaces between these larger grains. So we are looking at these yellow specks. So how many were there? So we were really happy with our FIB-SEM, but that did not give us like our distribution immediately, because the FIB-SEM wasn't, the volume of the FIB-SEM was not large enough to see the large grains. So then we had like a scan with all the tiny grains, and we had a scan with large grains, but we needed to connect the two. And then we made use of the property that all these tiny grains were on the interfaces of the large grains. So in the micro-CT scan, the same sample, like the sister sample, we calculated what the surface area of these large grains are. And from the FIB-SEM data, we calculated what the amount of small grains per surface area were, and then we just connected the two. So now we have a log normal distribution, and it peaks here with grains of about 80 nanometers, which is a bit problematic, because the resolution of our Microscopy just goes down to, well, this domain, that range. So that means that we missed the majority of our magnetic grains. So this is a bit puzzling, also because our inversions on these volcanic rocks generally do yield stable results for the larger grains. So yesterday I was, Andrew already brought it up that we might underestimate these vortex states or these double vortex states, or the grain size range that is right there, and that we can see in our micro-CT scan, because I personally do think that that's where the most of the magnetizations of these volcanics actually is in. Like these really tiny grains, there are many of them, but they are really, really tiny. Volume decays to the power of 3. So even although their magnetization might be higher than larger grains, because their volume is so small, they might disappear. So I really do think that we are underestimating these things that we previously referred to as PSD grains. But well, that is to be found out. We are working on Frank out, he's my PhD student, he's working on this. This should be published soon, and then we should do these modeling studies. So this is the probability density function a log normal distribution. So that's a formula. So, okay, cool. This is Frank. You might have seen him. He was in Chicago as well. So then, until then, we were used to fitting dipoles, because that's what we, well, generally think of. So we have a grain, and if we are far enough, then that signal becomes fully dipolar. But the QDM, by its nature, it's really close by. So you see these expressions of vortex states or multi-domain grains. So you cannot just easily fit a dipole without kind of underfitting your data. So David, my postdoc, he was working on these inversion routine anyway. So he said, well, then we can try and do Sverker harmonic fitting. So let's go back to this scan. This is data from first paper, 2018 paper. So this is scanning squid data, but for the inversion, that doesn't matter. Here we have like an area with only 8 distinct grains. And what we're looking at right here is this is the dipole inversion. This is the quadrupole inversion, and this is the octupole inversion. So in the left-hand column, you see the result of the inversion. So these signals are fully dipolar, and this is the residual. So this is the magnetization that we cannot explain if we fit dipoles. When we fit quadrupoles, in this case, the residual already goes down. When we fit octupoles, we can actually explain the complex magnetizations that we see on the surface, and the residuals are almost completely gone. So that's really cool. But then we started comparing these solutions, because in the ideal case, all these dipole components, like the dipole component you always solve for, even when you're also solving for higher order terms, well, in the ideal case, it should be constant. These should be the same. So in magnitude, that is true for many of the grains. So these are the 8 individual grains. The triangles is the solution that Carl and I made with our Fortran code that ran for 2 days. And then these blue circles are the dipole codes that David programmed that ran in 3 minutes. And then we have the quadrupoles that David programmed, and the octupoles. So for most grains, the solutions of the dipole component agree pretty much, but not for all. So that was a bit, well, we have to be careful with that. But then an important part. So this is the direction of the three types, so the dipole, the quadrupole, and the octupole solution. So we have these symbols for the 8 grains, and then the size for which solution it is. Like, and for many grains, like here the square one and this one, and here also these crosses, the directions are relatively stable. But for some grains, like this one, these 5, like thing with five corners thingy, they kind of jump from here to there. Also, the diamonds are interesting because this one is almost antipodal to the other 2. So that's where we have to be careful with choosing the solution. And also, if we want to interpret these things in terms of paleomagnetic direction, we first need to make sure which inversion is actually stable and correct. So which solutions we actually should select. But we can also plot this. So we have this is the first 5 grains in this data set, where we just showed you it's the first 5 were the most stable anyway. So if we would plot the magnetization on a little sphere that encapsulates the grain, so we have the grain on top, little sphere around it, then these are the dipole solutions. And then these are the quadrupole solutions. And here are the octupole solutions. So we see the magnetizations around these grains becoming more and more complex. So we have sometimes, so this is the grain that really changes direction. Sometimes they are quite alike. But the main take-home message from here is that we can have a look at the magnetization that actually on a sphere that encapsulates our grains. So this is all published. But then that made us wonder, we might be able to expand this towards a more fundamental rock magnetic study. Because what we did so far is we had the computed tomography, scanning magnetometry, and we calculated moments, either dipole or spherical harmonics. But what David did, he said, well, with Merrill, we can make micromagnetic models of grains. So we can model a large number of possible domain states in the grains, because we have the shape and the volume of these grains anyway from the micro-CT data. So he calculated possible magnetic configurations, and then he simulated the straight field signal that you would expect from such a magnetic configuration in the grain. And the straight field signal that we have here, that's something we can transform again, or translate again into these spherical harmonic descriptions. And then we can start comparing output, Merrill output, if you translate that to spherical harmonic descriptions, to the spherical harmonic descriptions that we have from visualizations from scanning magnetometry, which means that we might be able, if you're lucky, that there is one, or maybe more if you're unlucky, possible solutions from the Merrill modeling exercise that we did that actually compares to the configuration that we measured. So in that way, it might be possible to select the domain state or the Merrill model that corresponds to the domain state of these grains. So this is simulated data. It is not actual data yet, because there's one caveat that I'll discuss in a bit. So here we have a grain, nice grain with a double vortex state. And if you simulate the data, then this is what the magnetic surface scan on top of that grain would look like. So if you have this grain in that magnetic state, then that's the thing you would measure on top of it. So if you now take that data and we do a dipole inversion, well, that doesn't really fit, because a dipole inversion only gives you, well, a dipole, and this grain is surely not a dipole. So this fit doesn't really work, so you end up with a pretty high residual. But if you do the octupole inversion, then this map actually corresponds to the simulated surface map pretty well. So that means that your residual is almost gone. So in this case, the spherical harmonic expression of this and this state would be pretty much the same, and you could actually select your Merrill model based on the simulation on top of that. So it's David's work. He worked in our group for 3 years. He's continuing this work, but he has a postdoc in Santiago, his hometown in Chile. But he's still continuing on this work also in collaboration with our group. And started this week. So her main project will be to prove this in practice. So we have like a perfect theoretical framework, but Gu's going to work on like actually making these scans. Well, if you look really closely, there's one little issue, and that is that this has a surface area of about 4 square micron. And the resolution of our QDM is about 1 micron. So in a real QDM scan, this would go down to like 4 pixels. And then you cannot fit octupoles anymore, because then you lack a lot of data. We're working with people in Zurich, and they had the brilliant idea to put an NV center in the tip of an AFM probe. The main reason why you cannot get below this 1 micron resolution with your wide field QDM is because the diffraction limit. We're working with like light, fluorescence light, that has a wavelength of about 600, or from 600 to 800 nanometers. So you cannot go down that really far. It's a diffraction limit of the system. But if you know where your NV center is, then you don't need to know where the light comes from anymore. Any light that you measure comes from your NV center, and if that's is in the tip of your AFM probe, you know where your probe is, and that thing has a resolution of 10 nanometers. So that's what we're going to try. We might fail miserably, but then we learn something as well. Or it works, and we'll know that in 1 or 2 years from now. It would be really great, because this would actually bridge the gap between like Merrill modeling and actually being able to select the best configuration. Other things that we're going to do is we get working on Ishra dikes with Claire Nichols and Philipstein, Devonian lavas, Matt Domar. We were collaborating on Ediacaran volcanics, because until now it has been an academic exercise, and we want to really translate this now to having geological applications. So we're looking at these volcanic rocks right now. This is Project of Rosa, Rashida de Boer. Good thing that I want to mention, all the codes that David programmed are open source. So we submitted this to Computers and Geoscience, awaiting reviews right now, but David programmed everything. It's already on GitHub, it's already public, but the paper is a nice manual, so you might want to wait for that for a bit. But all the inversions that we do, including sensor characterizations, including anything we did, is open source and on our repository. Anything you want to find is on our project website. This is the team. That will be me, recognize me. That's Carl Fabian. And then sometimes he has been like my mathematical consciousness, because I'm not a mathematician. He is. David, programmer. Mike sadly left academia, but he is helping us out with QDM. Bunch of PhD candidates and the technician. And lastly, I want to plug the Castle meeting. I don't know, this meeting, IRM meeting, I think it left the continent only once, isn't it? A few times. Okay, twice. Okay, cool. In 2017, many of you were there. This is the fourth. We're going to have the Castle meeting there. Mark Dekkers retires, so that's the reason why we have it. And I think we're going to build like a couple of little towers, so we have an actual castle. But we will also do a summer school for PhDs, postdocs, with hands-on experience with our QDMs. So that will be in the first week of July next year. Shameless plug, but do mark your calendar if you would like to come. Thanks.
All right, thanks so much, Lennart. I think we have time for like the question or two.
Thanks very much for that talk. Just a quick question. What's the main limiting factor? Is it the micro CT scan resolution, or is it the magnetic scanning resolution?
For our volcanics, for the magnetic scan resolution, you can easily calculate, because for an octopole you need 15 variables to solve for. So you can calculate the amount of data points that you have, and the amount of grains that you have, and the amount of variables you need to solve per grain. And that system is still vastly overdetermined. Like, you have literally hundreds of data points per variable to solve for. So the resolution in the QDM scan with this 1 by 1 micron is perfectly fine. The thing that worries us most now is that because we know that we don't see, we have these ghost grains, we don't see them, and the inversions are relatively stable. So the next big step that we really need to understand is which grains in a volcanic sample actually contribute to its bulk signal most. And that's what we're currently looking into with these FIPSAM studies, and also, yeah, that's the modeling study. So this is the most pressing thing right now.
Okay.
Thanks. So I keep pushing you on the resolution issue. So you've addressed that, and the NV addition sounds really exciting. Your end game is to get paleo intensities, yeah?
Yeah, I assume that I'll have a lot more gray hair once I get there, but it's kind of yeah, my end goal would yeah, of course.
Okay. So then statistics, yeah.
Mm-hmm.
Presumably you're doing it particle by particle rather than bulk, yeah.
Yeah.
How many particles do you need to have results from?
Well, single domain, the grains that we don't see, millions. But I think, and I sincerely believe, that these vortex grains that we start seeing now with a resolution of 350 nanometers might be thousands, 10,000s, something like that.
Because they have enough moment.
Yeah, and their acquisition of their magnetization is, well, it's a statistical process, but it's not like with a single domain grain, it's like either that way or that way, you know, it's their easy axis. But for these vortex states, these grains have many more LEMs to choose from. So you have many more configurations to choose from given their, so I hope that you need less grains of them to have a statistical reliable ensemble.
And then in terms of a typical sample that you're scanning, how do you get that volume of material? You just measure more and more surface area?
Yeah, but the funny thing is that the sample that Marta scanned, and she scanned her resolution of her micro-CT scan was about 800 nanometers. That was before we found the really nice thing in Oslo. She has 1600 grains in a square millimeter. And a QDM scan is 4 square millimeter. So there are, that's like, what is it, 6,000 grains in a full QDM scan. And if we push the resolution, then more grains will show up in the same surface area. So it's not undoable.
And seeing your MD results and more grid, yeah.
And in a way, like, if we have, now I put these PhD students in a lab and tell them to throw away 80% of the data. There's a whole lot of time invested there as well. So if I could let them invest the same amount of time, but with a higher chance of better data, that would be an easy choice.
We have a question from none other than Rich Harrison asking, did you solve the issue of inversion being less sensitive to particles that are too deep in the sample, i.e. far from the center?
Yeah, that's a really good question. So if they're really close, then we see a lot of these multi-domain expressions or vortex expressions. If they're really, really deep, they start to disappear. That means that their inversion is going to be unstable. What we're now experimenting with, but that's very early, we are now using samples that are like 50 microns thick. We're trying to increase our thickness because then they become more sturdy, and we dissolve the glue and we just flip them over and scan them from both sides. And that in our model studies would greatly improve the resolution or the what is it, sensitivity of our inversion.
We should maybe move on to the next speaker now. Thank you so much, Leonard. And if you have more questions, then we got like